thought that I would first start with a small presentation about Réseau santé numérique, given that Dan may be slowly joining in also into the to this Quebec's network. And I would like also to invite you all to join the network so that we build a stronger community here. So this network saw the day was funded by FRQ since has been funded by FRQ since April 2024. So it's a pretty young network. There are 17, I believe, thematics networks funded by FRQ, and Réseau Santé Numérique Digital Health Network is one of them. So I'll try to present that to you quickly so that you can go also on the website afterwards. So rsn.quebec, and you can find much more information there. Also a subscription registration page to become a member. Feel free to go visit that. So I'm one of the five co-directors. We're five co-directors actually spread out in different universities in Quebec. I'll explain that to you. And we're slowly building our community, slowly but surely building our community. Actually, we're now have 700, more than 700 members in Quebec. Most are regular researchers, students. There are also partner members from the government, for example, or even citizens that sign up to this network to participate in the different activities and share their thoughts about how digital health could progress in Quebec. So the mission is really to be a catalyst for Quebec's digital health ecosystem. You can think that of as an entry door towards a door of entry towards the ecosystem of digital health research in Quebec. That's what we tell the government anyway. If they want to they want to find expertise in different aspects of digital health, well, they can come knock at our door first so that we can direct them towards different experts in Quebec. And we aspire to be the Quebec's voice, basically, yes, in digital health research. Yes, so we're our 7 pillars of activity, let's say, and I'll explain that quickly, but we want to create guides and tools in digital health. Map, right? Do a lot of mapping of the different members, first of all, their expertise, the different platforms, data sets, initiatives in Quebec revolving around digital health. So we're building tools actually so that it's easier to have a look at it and find the information. We're obviously connecting people together. That's the main purpose. One of the main purpose of the network is to connect people together. So enhance collaborations within the network, training the new generation of talents in digital health, just like you. Yeah, doing some consultation from the government. We have some mandates sometimes that the governments ask us to participate in different initiatives, different tables, expertise tables. So participate into that. Try to influence also the future of digital health in Quebec and organize many different events for that purpose, because digital health is quite large in its spectrum of activities, and we divide this into 4 different axes of expertise, 4 different axes of actions: digital platforms and information governance. So basically everything that relates to generating, managing quality and trusted data. 2, Axis 2, which is modeling digital tools, which goes from basic mathematical modeling, statistics, and to AI. So this all falls into this big axis of modeling and digital methods. Sorry. Axis 3, digital interventions in the real world and this life cycle associated to it, from design to implementation, adoption, and scaling. And last axis, which is more transversal to all those 3, about digital transformation, transformation of our organizations in Quebec, policies, systems, supporting those interventions mainly. We have different action fields. Okay, capacity building. A network is about building capacity, interdisciplinary training, knowledge mobilization, and it's guided by 5 different principles listed here, including open science, sustainable health, trusted digital methods, citizen engagement, and EDIA. That's basically the scientific structure of the network. So we're active in Quebec, obviously, but we're also doing partnerships with different initiatives in Canada and internationally. Notably, the new Canadian Vital project. Internationally, also there are initiatives about creating a network of networks in digital health. So we're trying to get involved into this. That's basically it here. And we have, as a network, we one of our main purpose is also to, okay, roughly speaking, also bring back the money to send back the money to our members in terms of call for projects, supporting project that support structuring between the axes, inter-axis projects, basically, axis 1, 2, 3, 4 that I just described earlier. So we have call for projects to support our members, our students, mobility scholarships, so that students from different places in Quebec can attend different events, for example, and different type of other initiatives to support members, communication grants, student scholarship supplements, and data to policy reports that we're building also. So these are the types of projects, so how we roughly speaking, send the money, spend the money of RSN for the benefit of the members. We have different events, okay, that were organized in the past. One of which was I think appreciated last September at the RI-MUHC, bringing together the platforms in Quebec, all the leaders of the different platforms in Quebec revolving around digital health. We plan to do that again this fall, so stay tuned. And there's different types of projects, like not of projects, of events, thematic semester on biostatistics, math santé. There are formerly student members, basically meant for students. So there's going to be a student rendezvous in this fall also. So you can, for example, register as a student member, and then you'll be on a separate student list, and the student committee basically has a certain budget to organize their own activities, and you can of course participate also to the larger RSN activities as well. We're going to participate also. We're making links with Digital Health Canada. So there's that. There's a something like a Digital Health Canada breakfast that is organized every year. So we partner with Digital Health Canada. We're gonna organize also different series of webinars covering the different axes in our program. And we're building a committee of practice. Notably, we're making links to bridge the community of practices also, actually between RSN and Mila at this moment. I was talking about the different tools we're building basically to map the initiative. So that's one of them. Different small tools, but useful tools to really understand the different organizations present in Quebec, the different data sets, platforms, how they are linked to the different researchers in Quebec, where they're located in Quebec. So that's all available on the RSN website to help understand a little bit better the ecosystem of digital health in Quebec. So we're a group of 5 co-directors, as I previously mentioned, one in Université Laval, 2 in McGill, and 2 at Université de Montréal as well. We have an executive team, so staff that do a very nice job for us to bring this all together, bring the network to life. So I always thank them very much to be working for us. And the core, basically, of the network, of the science of the network, is led by these people here, who are leaders of the different axes, the different action fields, and the different guiding principles. So that's professors in different universities in Quebec, leading the different scientific parts of the network. So basically, ASN is partnering with different entities in Quebec, in Canada, around the world, is also collaborating with the other thematic networks funded by FRQ. Most of them are listed here. Our members are from many different institutions in Quebec. And at the very center, there's different, in terms of capacity building, there's different platforms that we try to bring together to so that researchers can better know how to work with one or the other platforms, or how to combine the strength of the different platforms together, how to join them. So we're doing quite a bit of work on combining the strengths of these platforms. And one of these platforms is MEDomics, which is going to be the second part of this presentation. I'm going to present to you the one that is developed in my research lab, basically the platform MEDomics. So that's the upcoming part two of this presentation. So this is it for RSN, Réseau santé numérique. We're on LinkedIn. You'll probably easily find us on LinkedIn, Réseau santé numérique, and rsn.quebec is the main website where you'll find all the other information. Part about one of the platform, okay, in the RSN network, which is the one developed in my research laboratory. It's called MEDomics. It's a collaborative platform for medical data modeling. I'll try to explain that to you all right now, and I'll divide this talk into 5 parts. Try to describe the scope of MEDomics, provide an overview of what is MEDomics, and also give examples of key features inside the platform, and discuss to you about what's coming next this fall and in the next year, basically perspectives we have for MEDomics. Let's start with the scope of MEDomics. The overarching goal of, let's say, my lab or MEDomics in general, we want to do research and contribute to better precision medicine. And really, this is just a general quote. I'd like to bring it back in my talks like this, but it basically summarizes what is precision medicine, delivering the right treatments at the right time, every time to the right person. And we want MEDomics Lab to contribute to this. Some fundamental premises about how to contribute to precision medicine. I talk about sometimes democratic AI, how it can help, basically being transparent in its creation with different diverse stakeholders, including our governments, domain users, and so on. Interdisciplinarity is key, and maybe that's also why we have to collaborate all together, different research labs, your lab, my lab, and so that we can combine our strength to build better health AI. And MEDomics, I believe, allows or helps to provide better accessibility to AI, and I'll explain that later in the talk. Another fundamental premise is that generalist medical AI, to me, that's an opinion, is not sufficient, and that specialist and precision medical AI are also needed. And really quickly, that's one example that dates back, okay, still since 2023. You probably know this foundational model, MedPalm-M. Generalists, really roughly speaking, that's in the scope of, let's say, generalist AI, multi inputs, allowing multi different types of to solve many different types of tasks, multitasks, integrated within one system, MedPalm-M. So that's basically in the realm of generalist AI. Those huge and beautiful and very useful foundational models. Precision AI is also needed for precision medicine in the sense that we need models that are intrinsically adaptive to changing conditions for patients receiving different treatments. And for example, in oncology, how can we adapt basically our interventions? Obviously, that's what doctors do every day, adapt their interventions according to how patient responds. And we have also models that help that support clinical teams to do that. And that's the basic causal graph of medicine. Patients have different state X, or we observe different states of patients at different time points, which basically is this our set of features that influences how treatment are prescribed and are delivered, which obviously influence also the outcomes of patients. So that's a basic graph, causality graph here of medicine. So we need to be able to help in supporting the prescription of different treatments and different interventions. We need to infer some causal effects of these different interventions T, which needs to be done as a function of time as well. So when we get to this point, causality, causal modeling, that's what I described more about precision AI. And in between, there's what I call between generalist AI, precision AI, there's what I call specialist AI, and I'll get to this very soon, specialist AI. And this is just a slide to summarize that, or to show that the MEDomics platform that I'm going to talk about, which is focused, as you can imagine, okay, on as you can guess, on specialist AI. Well, it's at the center of the developments in my research lab. So my lab is called MEDomics Lab, very original, but the platform in itself is MEDomics alone. The MEDomics platform versus the research laboratory, which is MEDomics Lab, currently divided into two universities because I'm in transition from University of Sherbrooke to McGill at this moment. So I have students in those two universities. So this platform, MEDomics, is fueled by the developments in different aspects. Okay, software engineering, obviously, because it's a platform, you'll see medical image analysis, AI for health in general, but focus mostly on modeling and deployment. So different research developments that are meant to be integrated within the platform so that they are more accessible to other researchers and the community in general. So the scope of MEDomics, if I may finish on this first part of the talk, is about mainly specialist AI and the development of predictive models for specialized medical domains. The long-term plan is also to link this to and have better links to generalist AI, for example, have better links to those foundation models that exist. Also develop different types of have better accessibility also for users to develop different causal models and do continual causal learning. So in the realm of precision AI. And I think the glue that bridges all of those things, and you probably know even more than me about it, but it's agentic AI. So agentic AI may be the glue, could be the glue, is the glue, I think, that bridges those three different domains here together, generalist to specialist to precision AI, depending on the task at hand that is asked by users, for example. At this moment, MEDomics is really focused at the center here, but the plan is to expand to the left, expand to the right in the next years. That was the part one, scope of MEDomics. I'll go on with an overview of MEDomics. And for that, I have a video, first of all, that summarizes MEDomics. It dates back now since a couple of maybe a year and a half, so we'll have to update it, but it gives you a quick idea in 2 minutes. So I'll start the video right now.
Despite their essential role as experts, clinical researchers face challenges in accessing essential tools and collaborative channels to use AI more effectively. Bridging this gap requires empowering researchers with resources to drive AI advancements and fostering more collaboration between medical and computational fields. MEDomics is an open-source platform designed to support the research community and help medical AI teams to better work together. It addresses these challenges by, first, providing clinical researchers with easy access to AI tools, enabling them to independently run their own experiments. Second, by facilitating collaboration among interdisciplinary research teams, bridging clinical expertise and computational science. And third, by offering computer scientists an integrated environment with access to multiple state-of-the-art solutions. The MEDomics platform combines the power of multimodality medical data and a collaborative research environment to drive innovation in personalized healthcare. It empowers teams to develop predictive models for personalized treatments. The MEDomics platform offers versatile usage levels, from user-friendly built-in pipelines to highly customizable Python libraries, making it accessible to both clinicians and computer scientists. Its three core layers, design, development, and deployment, enable heterogeneous medical data integration, feature extraction, and model training and evaluation, all while supporting decentralized model validation, crucial for secure, collaborative research. Furthermore, the code generation feature is a highlight of the MEDomics platform, allowing users to automatically generate Python code from graphical pipelines, creating a powerful synergy between the medical and computational fields. Accessible on multiple operating systems, with comprehensive documentation and an active community, MEDomics is ready to support your journey in medical AI. Visit our website to get started and join a community dedicated to transforming personalized medicine through integrative data modeling.
All right. Okay. So that was MEDomics. I'll present again some slides that basically reinforce basically what was presented in the video. So why the name MEDomics? Med for heterogeneous medical data modeling. So we're doing MEDomics. Characterization of omics refers to characterization of biological processes. Here with heterogeneous, by modeling heterogeneous medical data, and the platform refers to that working environment that we're building. All with the main focus at this moment is of developing predictive models for personalized treatments. We want to help with this platform, with this software. We want to help medical AI teams to better work together. So that's really a view of the mind here. But having, for example, clinical scientists that may know maybe a little bit less about AI or coding expertise to still be involved as much as the computer scientist in data management, AI, defining AI hypothesis, doing the computing, visualizing, adapting the experiments all together within a single environment, basically. So we want to increase the synergy between clinical scientists and computer scientists in medical AI research. So increase synergy and interdisciplinarity between the research teams. And that's a very busy slide, but this is to say that MEDomics platform obviously does not do everything, cannot do everything. There's a lot of work being done, you know, just like the Canadian Vital Project to organize data and how we query data and how we use data basically for research. So that's one part on the left here. Once it's integrated into those MEDomics format that we're trying to expand so that they're so that we adhere to international standards even further. So once we're in, that's where interdisciplinary research teams can better work together. There's also a component on expert analysis, which is outside the scope of MEDomics in the sense that there's always going to be state-of-the-art research done in the world, in our domain, basically, but that we try to also integrate the results of these expert analyses, that we also try to integrate as much as possible over time in the platform so that it can be used by users of the platform. And the platform is divided into two. One front-end interface, okay, divided between layers, 3 layers. You'll see multiple modules that allows you to create experimental pipelines. And this is linked to a backend code, our own backend code with different packages that we integrate, different wrappers we create around existing packages. This is linked via code generator in the sense that you can create your different pipelines, your graphical pipelines for different experiments in the front-end interface and basically click a button to generate the code that is associated to those experimental pipelines. Those basically generate the code that is used to run the pipelines in the interface. So for those interested, there's that big front-end component versus back-end component. Here's the high-level architecture of MEDomics. The front end is based on Electron, Next.js, and React, and communicates with the back-end to the back-end of MEDomics, which is mainly in Python. This is the link is made with Go server. And our own internal way of handling multiple different data types is with MongoDB. Our databases are built on MongoDB internally. And we're currently building MEDomics so that it can be divided into two parts. There's the full application, but there's also the lightweight version, the MEDomics client, basically that you could install on your laptop. You can install everything on your laptop, basically, but the MEDomics, you could install only the MEDomics client, install the MEDomics server somewhere else, for example, in one computer in the hospital, for example, and express and do some computing requests on the MEDomics server remotely. So we're trying to have these two components separated so that you may use the lightweight client just on your laptop to communicate with a remote server. The local workflow or the general workflow is basically divided into three. We have a layer, design layer, where there's three main modules. One to extract features, so basically to go from different types of modalities like time series, images, text into tabular data. So feature extractor, and that's where you can bring in different pre-trained models, basically to extract features, extract embeddings right here. Explore basically your data with the exploratory module. And we have this input module basically to do data wrangling and prepare your data tables for downstream experiments in the development layer, where we have this main machine learning module, do the experiment, create final models, evaluation module to test, explain your models, and we also have a federated learning module to simulate federated learning as if we're doing these two parts here in a federated learning manner, in a distributed manner. That can be simulated also within the platform, and we're expanding this to do actually real calculations in the real world. So do real world federated learning here. That's coming in the next months, actually. And finally, we have a deployment layer where those models that are created can be shared basically between collaborators and can be integrated into the platform. So you can use the platform just to apply a model and see what it yields on what it provides on new patients, basically. That's the local workflow. The remote workflow that we're building now. So we have a full application where you have all the full components. You may use just the client locally, basically an interface based on Electron. We have this superset application integrated within MEDomics, which is basically the open source equivalent of Microsoft Power BI, basically, superset, which allows us, superset really is a magnificent tool to connect to different types of data, connect to different types of databases, connect, explore, import data, basically, with this tool. And we have, as I previously mentioned, that server, the MEDomics server, when you can use the client or the full application to run different experiments remotely on the server, retrieve the results of your experiments seamlessly so that you basically see everything in the client. And more and more now we're about to finish this work to do also to install multiple MEDomics servers, for example, in different hospitals, different locations, physical locations, so that we can manage federated learning experiment with one client in one local location. That's what the remote workflow looks like, and we're using different combinations of tools like Tailscale, Secret Shell, obviously, but WebSock is also too, so that this workflow basically runs smoothly. So MEDomics, the main website is medomics.app, the application, the software, the platform, medomics.app. And And from there, you'll have links to our GitHub, our open source code, our new releases. We're like at version 1.8.2, I believe, at this moment. We have our project board on GitHub where you can follow our developments basically and what we plan to do in the next in the future. You can post your issues there also. Our documentation is hosted on Gitbook. You have also links there to tutorials, demos. You have a we have a YouTube channel where we have those videos, okay, that describe that easier, maybe more easily describe how to do the different tutorials, and a Discord server also that you can join to come if you need assistance, come to chat with us at any time there. It's all available on MEDomics.app. That was the overview of MEDomics. I want to quickly now, I know time is running fast. I want to go and show you two key features in MEDomics. One of them is about integrative modeling. So MEDomics is focused on predictive modeling at first. When we do predictive modeling, we do one huge and reasonable assumption is that we don't model basically these links between X and T and Y. We assume basically, and that's reasonable also, that all patients receive the best possible treatment according to their state X. So we're trying to find relations basically between X and Y, the state of patients and their outcomes. Basically modeling P of Y given X, developing a function providing the probability of observing an outcome Y given a state of a patient X, so that we can have and provide an improved assessment of patient state X at a given time point. One example of a specialized predictive model in a specialized medical domain is to predict lung metastases. When patients come to the hospital in oncology, they have soft tissue sarcomas, one specific type of cancer, trying to predict as soon as possible the likelihood that they will develop lung metastases, which is a huge one of the big problem in managing those types of cancers here. This type of cancers, these types of tumors, soft tissue sarcomas. So what would be X for solving this problem and providing this assessment of likelihood of developing lung metastases? We could analyze images, we could analyze text reports, we could analyze multi-omics profile if it's available. We could obviously integrate demographics information into the models as well. This is multimodal data. So how to combine these different different types of modalities together, that's one challenge, and that's what we try to make this process easier actually within the platform. And actually, that's multimodal data. I prefer to really call it heterogeneous data in the sense that they're acquired at different biological scales, basically. And to me, it's better described with the word heterogeneous data. But the question once we have this is how to model X, how to create that function that maps X to Y. The core algorithm we use in our work within our platform is graph neural networks. Basically, neural networks, but that combine the power of neural networks with relational inference of graph models. So with graph neural networks, we can also exploit relations between variables, between features, and between patients, and combine this in multi-level graphs, basically, where we can exploit those useful relations within the models. So with that, what we're trying to do is to not only model medical data as multimodal, but as hierarchical also, coming from different acquired and describing different biological scales, basically. So we try to take these scales, these hierarchical scales into account when we do modeling, and that's what we call integrative modeling. And that's what we're implementing in our platform right now, so that it's easier to define those scales and do the modeling according to those scales. So modeling the hierarchical nature of multimodal medical data when we try to learn patient representations for different tasks at hand, for different tasks that we want to solve, for different predictive models that we want to build. And in the future, also, we plan to add a reinforcement learning layer here to discover different cross-modality interactions that could be useful for different predictive tasks. So that's one key feature of MEDomics, and that was in the modeling component of MEDomics. Another huge component, I would say, of MEDomics is about being able to easily evaluate the different models that we create, and that's done with the evaluation module. And we integrate another key feature, which is precision analysis. So precision performance predictive analysis. This should be predictive analysis here. And what is this thing here in the evaluation module? Well, we want with our evaluation module to be able, once we have a model that exists, to be able to develop when a model actually should not be used, basically. Detecting when a given model should not be used for different types of patients that were maybe not different profiles that were not present within the training data. So here's a model that really separates these two classes in 2 dimensions and with a two-dimensional feature vector here. That would be a model, okay, a simple line. This simple line would not work well, for example, when we evaluate or deploy that model into a new institution. We want to detect when a given model should not be used, for example, for that specific type of data here, this data cloud here. So we want to provide tools to do continuous evaluation of predictive models per patient profile. So what's a patient profile? To usually when we assess the effectiveness of a model before deployment is usually with by recording global performance matrix on a full evaluation set. But we want to also provide the information about does it perform well in different subgroups of that full evaluation set. So let's say on the full evaluation set, we could get a good performance metric, AUC of 0.90. That's very good. Okay, but we want to decorticate, basically, subdivide this prediction performance into the different patient subgroups, patient profiles forming this full evaluation set. And that's just an example here, but this 0.90 could be divided into 0.70 for the specific subgroup, here female, for example, and 0.95 for male. And we can go on and make more precise patient profiles as well and decorticate basically the predictive confidence, predictive performance, and predictive confidence for the different subgroups within the full evaluation set. So we believe this can help us to detect performance shift, detect biases per patient profile. So basically provide tools so that this evaluation can be more easily done by researchers. And that's called MEDGPA, Predictive Performance Precision Analysis in Medicine. That's the tool that we integrate into MEDomics. And I'll go quickly here, but basically the idea at the end, sorry, I'll go a bit quickly here, but the idea at the end is to, when running MEDGPA, it's the potential clinical use basically is to say, okay, we have that performance for different subgroups, good, but we also have that predicted confidence level, basically, that given predicted confidence. So you may have, okay, some predictive probability that gives you some answer here, let's say 0.74%, that you, for example, here, P of y equals 1 here, which is the risk of mortality after 1 year. So it would be 0.74, but with a very low confidence level about the prediction in itself. That's what MEDGPA gives you as an output. So even though you have this prediction probability here, you have very low confidence level, so you would reject basically the use of the model in itself. And you would not use the model for that patient subgroup, for example. And we try to make different levels of confidence. So reject the prediction, be careful with the prediction, or the prediction is approved no matter what the prediction is actually is, but really approve it based on the confidence level of the prediction. So that's the supplementary types of tools that we try to provide when we evaluate models, so that these model predictions are also complemented by predictive confidence, by patient profile, so that we can continuously validate predictive confidence over time and externally when we deploy models in different institutions. That's basically the other key feature in MEDomics. It's that MED3PA, predictive performance predictive analysis. This package integrated into MEDomics in the evaluation module. And finally, last part of the talk, future perspectives of MEDomics. At this moment, as you've seen also in the video, our experiments are basically static. It's a set of different modules interconnected together, but still, you still need some expertise basically to navigate between the different models. So there's no basically AI assistance that helps you to navigate within all the different tools of the different platforms that helps you to make the connection between the different modules and tools on the platform. Basic output of those of MEDomics is basically models, predictive models that you can share with your collaborators. That's very, very good. Okay. Pipelines that you can share with your collaborators so that they don't start from scratch but can adapt on their own data set. And experimental code. So you create your pipelines, it works, your models, it works, good. You can also create the code associated to it so that others may refine it afterwards. That's all very good, but that may not be sufficient in the world we live in now. Sharing specialized model applications to the community may not be sufficient anymore. We want to upgrade basically this box here with specialized agents, as you can imagine, so that these agents can be later on, instead of sharing models, we want to share agents that could be used by others, and linked to external larger scale agentic AI health systems if needed, if they want. And to do that, so that people can develop those agents, we want also to create that so that it can be all done locally. So you've seen that we have this way of working where we want to provide as much tools as possible for people to work in the hospital and do that locally. So this creation of agents also, we want to provide tools for users to do that locally. So without calls to external APIs, if they want, if they can connect to other external APIs, that could be possible too. But we want to provide the possibility to do everything locally as well. So the plan in the next months, the next years, is really to facilitate user experimental development with really lightweight, local and lightweight assistant agentic AI system. Facilitate the creation of, again, lightweight specialized AI agents or skills as outputs to our experiments, so that the main outputs basically of MEDomics now would be first, the whole workflow of MEDomics would first be guided by AI. And we would have more useful outputs, not just specialized models, but also specialized package AI agents and skills that can be reused by others and shared. Sorry. So in the end, we saw this local workflow earlier. The idea to upgrade this in the next year and next 1 or 2 years, basically, is to basically create agents out of those modules. So each module will become a specialized agent so that it can be better interconnected and better powered also by a local orchestrator between those multi-agents here, so that the user can more easily navigate between the different modules and tools of MEDomics. And the other main component that we want to have is, okay, not only share models, but that the output of what you create within MEDomics is actually specialized agents or specialized skills for different agents. So that's the main changes basically that will happen in MEDomics in the next 1 or 2 years that we are planning to do. So to summarize, precision medicine, as I discussed at the very beginning of the talk, needs specialist medical AI, but specialist medical AI also involves complex modeling workflow for specialized tasks. And to do better research and model those complex workflows, it requires interdisciplinary research synergy between different labs, for example, research labs with different expertise. And we believe, and what we were designing MEDomics to increase the synergy between interdisciplinary research teams. And in the future, MEDomics, this platform will be improved with local agentic AI capabilities. So that's what I had to say. It's an open source project developed by the community MEDomics, so feel free to join, to go on GitHub and contribute, send us improvements, or simply contact me so that we can work together. It will be my pleasure. Thank you very much for your attention.